Hey everyone, in this video we're going to be using triple integrals to find the formula for the volume of a sphere. So triple integrals are another multivariable calculus technique, and in this one we're going to be using three integrals, and we're going to be using a full sphere to find the volume. So again, like in the last video when we used polar coordinates instead of regular double integral, we're going to be using spherical coordinates here instead of a regular triple integral because it will make our calculations a lot simpler. So we're going to start with the form for spherical coordinates, which is our three integrals and our three limits. So d rho, which is what's that called? D phi or phi, and d theta. And of course we have to include the interior term, which is rho squared sine of phi. So now what are our limits for rho? Rho is going from 0 to a. What are our limits for phi or phi? It's going from 0 to pi, because it's going phi is always measured from the positive z-axis to the negative z-axis, so it's going the full angle from 0 to pi. And theta, we know, it's measured from the positive x-axis, and it goes all the way around again. So again, that's 0 to 2 pi. So now we're going to go ahead and try to solve this integral as it is, because there's no f of xy in here, because with triple integrals it's already assumed to be a volume. That's what it means. It's taking little individual cubes of this solid sphere, whereas when using double integrals it was a hollow sphere. And we're adding up all these little cubes over all this big region, and when we add up those cubes we're going to be getting the volume. So let's start. So the first integral, the inside integral, is with respect to rho. So it's going to be 1/3 rho cubed sine of phi. And that's evaluated from what? From 0 to a. So it's going to be 1/3 a cubed sine of phi. And now we have two more integrals to evaluate: 0 to pi, 0 to 2 pi, d phi, d theta. This 1/3 a cubed we can move to the outside because it's a constant. Remember, our radius a is a constant, so we're going to move it to the outside so we don't have to deal with it all the way in there. And we're going to integral from 0 to 2 pi, integral from 0 to pi, sine phi d theta. So now sine of phi, which take an integral of that, it's just going to be negative cosine of phi evaluated from what? 0 to pi. So negative, move the negative outside. Cosine of phi is negative 1 minus cosine of 0 is 1. So it's going to be negative quantity negative 1 minus 1, which is going to come out to a 2. Again, this 2 is a constant. We're going to move it to the outside of the integral with a 1/3 a cubed. So it's going to be 2/3 a cubed integral of from 0 to 2 pi and just d theta. So now when we integrate this, we're going to have theta, because this is actually just an imaginary 1 inside here, and that comes out to theta, evaluated from 0 to 2 pi, and that comes out to 2 pi. And this 2 pi multiplied by our 2/3 a cubed is 2/3 a cubed times 2 pi, which comes out to 4/3 pi a cubed. This is by far the simplest, most elegant way to solve for this volume, because it uses the full advantage of how to find the volume. It takes those little tiny cubes and just approximates them and finds the whole volume, rather than revolving some area or using some region underneath a solid. So now we know where that elementary formula for the volume of a sphere comes from. So hopefully we all learned something. Thanks for watching.